Gadgaon, Pune. Today, I represent here the Pharmaceutical Emulsion Part 2. In Part 1, we have discussed the beginning of the emulsion, its types, its advantages, and the different identification tests of an emulsion. Today, after completion of this, you are able to learn what do you mean by the emulsions, the emulsifying agents, mechanism of emulsifying agents, classification of emulsifying agents, and various theories of emulsion. So, as we discussed earlier, emulsion is a biphasic system that consists of two immiscible liquids, one of which is finally and uniformly dispersed as globules throughout the other. So, basically, there are two types of an emulsion, whether it may be a OW type of an emulsion or whether it may be a WO type of an emulsion. Now, the basic component in an emulsifying agent are the emulsifying agents, without which we can't prepare the emulsion. Emulsifying agents are the chemical agents that are used to reduce the coalescence between the two immiscible liquids. Coalescence means it is the aggregation of droplets which are after them lead to the instability in the emulsion. There are a number of emulsifying agents are available. So, depending upon which type of emulsion we have to prepare, we have to select the emulsifying agent. Whatever the emulsifying agent that you are selected for the pharmaceutical emulsion should have the following properties. First, it must be compatible with the formulation ingredients. Second, it must not interfere with the stability and efficacy of our product. Third, it should be non-toxic. Fourth, it should be stable and not deteriorate in the preparation. It should be odorless, colorless and tasteless, and it should increase the viscosity of the product. The increase in the viscosity of a product are required in order to maintain the stability of the emulsion. So, then we discuss how these emulsifying agents are responsible for the formulation of an emulsion. So, when two immiscible liquids are mixed, they are formed in separate layers, and the surface free energy of the system is increased due to the interfacial agent, the different densities of two phases and the large surface of an dispersed phase. In order to stabilize it, the emulsifying agent is added. The emulsifying agent first adsorbs at the surface or interface, and when interface becomes saturated and no further space remaining, then this emulsifying agent moves toward the bulk of the solution. The emulsifying agent makes the two phases miscible in a manner that lipophilic portion of it is towards the oily phase and hydrophilic portion of it towards the aqueous phase. Micelles are formed at the CNC, which consists of 50 to 150 molecules of an emulsifying agent, and at this point the emulsification can occur. So, according to various theories of an emulsifying agent, these are stabilized the emulsion by reducing the surface tension, reducing the interfacial tension, form the film around the droplets, or it provides the electric potential. Now, depending upon the nature of an emulsifying agent, they are classified each into the different types. The first, naturally occurring materials and their derivatives. This is again divided into two types, whether it is obtained from vegetable source, for example gum acacia, tragacanth, agar, starch, etc., or it may be obtained from the animal source, for example egg oil, gelatin, wool fat, etc. Second class is semi-synthetic polysaccharides, for example methyl cellulose or carboxymethyl cellulose. Third class is synthetic synthetic surface active agents. Depending upon charge, this is again classified into four types. First is anionic. In anionic, there may be alkali metals and ammonium soap, for example sodium stearate. There may be the soap of divalent and trivalent metals, for example calcium oleate. It may be the amine soap, for example triphenylamine. Or it may be the sulfated and sulfonated compounds, for example sodium lauryl sulfate. Second class it is cationic surfactant, for example quaternary ammonium compound and cetrimide. The third is non-ionic, and these are most commonly used since it is less toxic as compared to the other, for example glycerin monostearate and glycerin monooleate. Fourth one, it is amphoteric, for example lecithin. The fourth broad class of emulsifying agent is inorganic, for example milk of magnesia or the magnesium oxide. And the last class it is alcohols, for example carboxyls, lecithin and cholesterol. So the number of scientists propose the different theories which explain how these emulsions are formed. So there are various theories, for example surface tension theory, oriented wedge theory, plastic or interfacial film theory, monomolecular absorption theory, viscosity theory and electrical double layer theory. So first we discuss surface tension theory. According to the surface tension theory of emulsification, the emulsifying agent causes a reduction in the interfacial tension of the two immiscible liquids, reduce the repellent force between the liquids and withdraw the attraction of an liquids for their own molecules. In this way, the surfactant converts the large globules into the smaller ones and also avoid small globules from coalescing into the large ones. Here in a diagram we can see that when we add the two phases of an emulsion, it is separated out. When we add an emulsion of phase B, they have to be dispersed in a phase A. After a certain period of time, we can say that both the phases are tried to separate. But when you add the emulsifying agent, it places at this interface of an globule between the phase A and phase B and thus stabilize the emulsion. Second theory, it is a oriented wedge theory. We are called it is oriented wedge theory since there is a formation of an wedges or curve around the emulsion globule. This theory assumes the monomolecular layer of emulsifying agent curved around the droplet of the internal phase of the emulsion. In a system that contains the two immiscible liquids, the emulsifying agent is preferentially soluble in one of the phases. Because many molecules of substance upon which the theory is based, here we are considering the soap as an emulsifying agent which have the hydrophilic head and hydrophobic tail. The molecule positions or orient themselves into each phase. Generally, the emulsifying agent having a greater hydrophilic than hydrophobic character will produce OW type of an emulsion, and a WO type of an emulsion result from the use of an emulsifying agent that is more hydrophobic than hydrophilic. So here we can say that when you add the emulsifying agent, there is a formation of such a monomolecular layer and there is a formation of an curve, or you may say that the wedges. And when we discuss, depending upon the solubility of an emulsifying agent, they are oriented themselves towards the each phase. The third theory is a plastic or interfacial film theory. In this theory, it places the emulsifying agent at the interface between the oil and water, surrounding the droplets of the internal phase as a thin layer of film. which is adsorbed on the surface of the drops. The film prevents the contact and coalescence of the dispersed phase. That means, tougher and more pliable the film, the greater the stability of the emulsion. Naturally, enough of the film forming material, that is the emulsifying agent, must be available to coat the entire surface of each drop of the internal film. Here again, the formation of an OW emulsion depends on degree of solubility of the agent in two phases. With water soluble agent, it will produce the OW emulsion, and oil soluble emulsifier produce the WO type of an emulsion. So here we can say that the same orientation, here it is the example of an OW type of an emulsion. So oil are surrounded by the emulsifying agent. Each droplet are surrounded by the emulsifying agent. That's why it will form a barrier and there will be no coalescence between the droplets. Next theory is a monomolecular adsorption theory. Surface active agents are the substances that are having the ability to adsorb over the surface. After adsorb over the surface, it will reduce the interfacial tension and it will lead to the formation of a monomolecular layer. This surface active agent we will call as an anthophiles. Thus, they are hydrophilic as well as lipophilic. Means they are having the hydrophilic head and the lipophilic tail. So when you add the emulsifying agent, it will form such a kind of a monomolecular adsorption theory, due to which the interfacial tension are reduced and it will lead to the formation of an emulsion. The next theory is a viscosity theory. This theory of an emulsion said that due to the increase in viscosity, it will produce the mechanical hindrance to coalescence of the globule. As per this theory, an increase in viscosity of an emulsion will lead to an increase in the stability. This theory we can particularly use for the emulsions that are prepared with the gums. For example, acacia, chagacan as an emulsifying agent. This theory particularly applied for the stability of an emulsion. There is a one limitation of this theory, that it failed to explain about the milk. Milk, it is a natural emulsion, but it is having a less viscosity, still it is stable. So this theory failed to explain how it happened in case of a milk. The last theory is an electrical double layer theory. Electrical double layer means there is a formation of an double layer around the droplets due to the adsorption of an charges. Electrical double layer consists of two layers, diffuse layer and tightly bound layer. So when oil globules in a pure oil or in a water carry the negative charge, as the water ionizes into the hydrogen as well as an hydroxyl ions, so if the oil absorbs the negative charge on the oil, due to the absorption of an OH minus ions of an water, thus there is a formation of an electrical double layer. In a diagram you can say that this is the oil droplet which absorbs this negative charge, so automatically the positive charge ions are get attracted and there is a formation of this electrical double layer, which is act as a resistance for the coalescence of the droplets, and thus it will stabilize the emulsions. So here we are discussed how the emulsifying agent forms the emulsions.